Welcome back to Physical Science 20. Last lesson was about specific heat capacity. That would have been found on March 17th. So today's lesson is going to focus on thermal equilibrium. That would have been March 18th. So again, the notes should be online if you want to just read through them. The questions will be similar to what you would have clicked on yesterday. There's also a resource package if you want to do some reading on your own. Forgive me, once in a while I'm going to clear my throat. So let's get into today's lesson. So last class was all about specific heat capacity. Now I'm going to show you where that comes into play, and that's when you take two substances and you mix them together. And so the law of conservation energy states that in any transfer or transformation of energy, the total amount of energy remains constant. So that means if you add a hot substance to a cold substance, the hot substance is going to lose its heat energy to the cold substance. So the cold substance will gain that heat energy. And while the hot substance cools off, the cold substance gets warmer. And that is seen as thermal equilibrium. But simpler to call it mixtures because you're just mixing a couple of things together. We'll keep it simple. We're just going to mix two things together in all of our scenarios. But obviously you can mix many things together that are all at different temperatures. So the simple equation to work with is the amount of heat energy lost by the hot substance should be equal to the amount of heat energy gained by the cold substance. So since the hot substance is going to lose energy, typically it should be negative in the end. But if we look at their absolute values, they should have the same magnitude of energy transformation. So if we actually add them together in their own separate equation, the amount of heat lost by the hot substance when added to the heat gained by the cold substance should amount to a total of 0 overall energy gain or loss in this system. So this is theoretical physics for the most part, because we're going to ignore any loss of energy due to radiation just going out into the atmosphere. If you've ever held a hot cup of hot chocolate, you know that you can feel the heat in the cup itself. If you put your hand over top of it, you can feel that the heat is escaping out of the top of the cup as well. So that is energy that's being lost. That would not be applicable to this equation. There would be another parameter you have to input in there, and that would be the air. But we're going to ignore that and just assume that no energy can be lost in those regards. Just for theoretical purposes, you can worry about reality when you get into those higher level physics classes where you're trying to figure out efficiencies. But that's a different topic for a different day. So for now, we'll keep things simple. When you add a hot thing to a cold thing, they're going to exchange energy until they reach the same final temperature. So basically what that means is we're going to take the equation from last time, your Q is equal to MC delta T for a hot substance and Q is equal to MC delta T for a cold substance, and add them together. That is the nature of thermal equilibrium. So you were also given last class a chart of specific heat capacities. All of those specific heat capacities were found by something called calorimetry. So that's where you add, so for instance, if maybe I had a cube of aluminum at one temperature and I had a vat of water at a different temperature, I would add that cube of aluminum into this vat of water, and I would just witness the overall change in temperature. And from that, I would be able to figure out what each of their specific heat capacities were. So that is something they use to figure out all these values. We're not going to do one of those, obviously, but that is the process in which we're going to base everything on. So from there, you probably witnessed this in your bathtub or your hot tub. If you jump in your hot tub, it's going to feel very warm because your hot tub is 42 degrees Celsius and your body temperature should be around 37 degrees Celsius. So it's going to feel great. The heat is going to go from the water and into you. And that is just basically due to your second law of thermodynamics. The flow of heat energy is always going to go from the hot to the cold. So that's going to feel great in your hot tub. If, for instance, you jump into a pool or a lake and it's maybe, I don't know, June or July, the outside temperature might only be 20 degrees for a month, and that means the water might only be 20 degrees. It's going to feel cold. So if you're sitting in a tub full of colder water, not that 20 degrees is overly cold, but it's colder than you at 37 degrees, you will shiver and it won't feel very great because you are now the hot source in this mixture. And so your body is going to lose heat energy to the water itself, and it's not going to feel very great, which is why we usually like our bath water to be a little bit warmer, or hot tubs, for instance. So those are just some common examples of thermal equilibrium. You would probably notice that with hot chocolate. If you add marshmallows to your hot chocolate, the hot chocolate will actually drop in temperature a little bit. Same thing if it's too hot and you burn your mouth and you burn your tongue. You might cry a little bit and get mom or dad to come rush in and give you some milk and put some cold milk in there, and it'll drop the temperature of your hot substance by a bit. And by process of doing that, the cold milk will actually get warmer, and you'll have a overall final temperature where the hot chocolate is cooler and the milk is warmer. Maybe you've experienced that in life, maybe not, I don't know. So what does that mean for us? So here's a little scenario that I'm going to walk you through. So how much mercury at 100 degrees Celsius must be added to 1 kilogram of water at 10 degrees Celsius to give a final temperature of 34 degrees Celsius? So I don't imagine you have a handful of mercury at 100 degrees at your disposal to do this practically, but it's just a scenario very similar to the hot chocolate and the milk. So when we have a question like this, there's multiple parts to it. So we need to kind of have two different categories when it comes to thermal equilibrium. I usually like to separate things into two categories, hot and cold. You have a hot substance, you have a cold substance. So my hot substance in this case is going to be my mercury. So mercury on your chart, which is from the print off, I showed you where it was, should be around 140 joules per kilogram degrees Celsius. And I also have water. Water is 4.2 times 10 to the 3, so 4,200 joules per kilogram degrees Celsius. That just comes from your chart. So hot substance, how much mercury at 100 degrees? So that's my hot substance, mercury. Mercury, the symbol, of course, is Hg. Must be added to a kilogram of water at 10 degrees. So 10 degrees is much colder. I'll just call that my cold substance. So these are relative hot and colds, depending on the question we're talking about. So the next thing that I want to focus on is the question asked, how much mercury? So we don't know the mass of mercury, okay? Must be added to 1 kilogram of water. So we know the mass of water. That's the next thing we point out. From there, we know the temperature, initial temperature of mercury, it's 100 degrees Celsius. We know the initial temperature of water, and that should be 10 degrees Celsius. So we put those down. And when it comes to thermal equilibrium, whenever you have a thermal equilibrium problem, that basically means your final temperature for both substances should be the same. So it should be the same parameter on both the hot and the cold. So in this case, it says in the question to give a final temperature of 34 degrees Celsius. That means the final temperature for the mercury when the water has been added should be 34 degrees. The final temperature of the cold water when the mercury is added should be 34 degrees. They come down to the same overall final temperature because there was an energy exchange. The hot thing gets cold, the cold thing gets hot. Well, relative. So write out your change in temperature equations, final minus initial on both sides. We have a subscript 1 for hot. I have a subscript 2 for cold. Just that's the way I set my problem up. I don't give a subscript to my final temperatures because it should be the exact same value. Just plug those in and you'll see that you have an overall temperature change of my mercury to be negative 66. That negative is important because it dropped in temperature, and my change in temperature of my water should be 24 degrees Celsius. So Remember, in the end, we're looking for how much mercury. So I'll just put a little circle around that to remind you it's a different color too. It's a reminder that that's what we're looking for in the end. So if I minimize that, just leave it in the corner in case you need to reference it again, or you can pause this video and go backwards at your leisure. But I'll try to keep this in the little corner there. So since we're doing thermal equilibrium, I've color coded it just to kind of remind you that Q1 is my hot, Q2 is my cold, and that was just what I decided. You don't have to make Q1 always the hot one. You don't have to make Q2 as the cold one. It's just how I set it up. So since we're doing thermal equilibrium, recognize that this delta Q is from your specific heat capacity, MC delta T, but it's for the hot substance. So I put a little subscript 1 for each of them, and likewise a little subscript 2 for each of those. Since I'm finding my mass of my mercury, I need to basically bring all of this of my cold substance to the other side of the equation. So therefore, I'm going to subtract both sides. And in the end, it just looks like this. So if you subtract M2C2 delta T2, it'll just be negative on the right-hand side. So my next step is to get the mass of the mercury all by itself. So I have multiplication between these three terms. So now I need to divide them out. So my specific capacity of mercury and my change in temperature of my mercury needs to be divided out. It will look like this. So you can cancel them off on the left-hand side. And I'm just going to have it rewritten. I erased the step and just rewrote it. But again, you can just go back if you need to see it. So I'll leave this on. Once you have this as your final equation, you can just start plugging numbers in. You know what they are. So mass 2 was 1 kilogram of water. C2 was your specific heat capacity of water. Delta T2 was your change in temperature of your cold water. So that should be in the numerator. Do not forget that negative symbol. A lot of people forget the negative symbol to carry it forward. So I'll just leave it in a different color. The denominator should be your mercury. So that's the specific heat capacity of mercury. And you have your negative 66 degrees Celsius as your temperature change of the mercury. Again, that negative is important because you need to cancel both of these out. Mass should never be solved as a negative value. So next little screen is all the cancellations. This negative gets canceled by that negative. The units for the specific heat capacity of the water get canceled by the units of the specific heat capacity of the mercury. The units for your degrees Celsius for your temperature change of the water should cancel the units for the degrees Celsius for your temperature change in the mercury. So those units will cancel out. The only units you should have left in the end should be the kilogram, and the rest is just mathematics. You punch them through your calculator. You'll probably see something around the likes of 1,800 kilograms because the kilograms get left over, divided by 909,240. No units left in the denominator. So you do some quick math and you'll get about 10.9 kilograms, if I rounded that correctly. Now I'll just look at the question real quick. I have 2 sig figs is probably what I'm going to have in the end because if you remember your rules for significant figures or significant digits, when you're doing multiplication and division, you should represent your final answer with the least number of significant figures. So 2 in this case, which means I have to make a quick little adjustment. And so we'll call it 11 kilograms of mercury is needed just to change the temperature of water by 24 degrees Celsius. So you will need a lot more mercury than you would water to change that temperature because mercury, again, has a very low specific heat capacity. Again, it is only 140 compared to water's 4,200. So you will need a lot of mercury before water is going to change its temperature. I'll stop there for now. I believe there's another question that you can read online on how to calculate the final temperature. It's a bit more difficult. If you have questions about it, I'll definitely answer anything you might have. You can either just email it to me, take a picture of it with your phone, how far you got or what you don't understand about it, or send me a little video response. That's entirely up to you and whatever you're comfortable with. Okay, we'll stop there.